My name is Enrique Mendes, and I'm here. I'm a product engineer for Tessent Embedded Analytics with Siemens EDA. Over the past few years, Tessent Embedded Analytics has worked with different companies in providing them debug and trace capabilities for functionally complex systems. In today's presentation, I will demonstrate the concept of using Tessent Embedded Analytics for functional monitoring in concert with sensor information to further debug and detect complicated issues in life. With the increasing demand and applications involving generative AI, as well as high-performance compute, as well as the move for multi-chiplet design, systems have increased complexity. And so with that increased complexity, figuring out issues, it becomes increasingly complex. Silent data corruption and timing-sensitive bugs are difficult to root cause without the right in-depth visibility. So it's also important to mention that going beyond just monitoring the processor core, it's important to monitor other parts of the system. And it's also important to have efficient monitoring at that. And with that, concepts like cross-triggering, which we'll explore, are quite important for that. Lastly, diagnosing issues in real life can present its own sets of issues, so there might not be access to a debug port. Also, the environment is not so controlled as it is in labs, so different issues can arise. So Tessent Embedded Analytics provides, as part of their Tessent UltraSight product, a full system level debug and functional monitoring by providing different IPs such as status monitor, process analytics model, trace encoder, so different solutions in order to really monitor a system of different levels of complexity. So to further expand on the concept of efficient functional monitoring, given the example of a traditional trace situation, we are left with large amounts of data, which can be quite hard to manage for a user when really the events that they're interested in tracing are sort of rare occurrences, such as a deadlock scenario. So by having embedded Tessent Analytics use cross-triggering and being triggered by that specific event, using their internal buffers, rolling buffers, we can actually obtain some information of what happened before, during, and also after the event. And this will help us understand what really happened. So going into an example of a multi-sensor approach to diagnose issues. So key challenges in modern systems include workload and predictability, and also voltage instability. AI models create different bursts of activity, and that can saturate the network on chip as well as memory controllers. And in terms of voltage instability, as technology nodes shrink, metal interconnects become more resistive, and high power density in AI as accelerators can lead to voltage events, and those can cause issues ranging from a timing issue or even permanently damaging silicon. So while providing monitoring provides methods to observe and debug system level problems, it doesn't have the visibility to detect such events such as voltage, such as in voltage domain, voltage profile. This is where having a concurrent set of multiple instruments in life can provide data to monitor, detect, and diagnose these anomalies and give actionable insight. So for example, if an SoC is embedded with voltage droop sensors and also functional monitors, we can have a system where the voltage sensor can sit vigilantly waiting for a voltage droop to happen. And when that happens, we can then enable our functional monitors, and that could help us diagnose what happened. So in collaboration with Movellus, we developed a system to sort of demonstrate this and how this could work in life. So we consider a multiple core system. We also instantiated the Movellus Aeonic inside Droop Detector, in which we can program different thresholds for voltage. So we set so that if a voltage goes beyond a certain threshold, an event output is generated. So then we took that event output and we used that as a trigger for our embedded analytics IP to start monitoring. So with that, we instantiated buzz monitors to monitor the activity to the main bus, as well as status monitor to monitor the activity on the Droop detector. And once all this data is captured, it is timestamped so that we can correlate all these events. So we then were able to instantiate a Droop model from Movellus in an FPGA along with our Tessent Embedded Analytics IP to sort of illustrate what could happen. So in this example, we can see that the first Droop actually enabled our functional monitors. And we started getting real in-time metric from the bus and the workload. In this case, we're considering access to memory when we're talking about workload. And so further along this situation, we can see that the bus monitors went from idle. They were waiting for this specific event, and then they are now working. And then we can see that an increased activity in the main bus is reported in real time by the bus monitor. We can actually see it going from 15% bus usage to around 35% in this case. And so a bigger voltage droop can then be observed, and this would seem to correlate. And we know that increases in workload can cause voltage droop in such systems. So through this example, the user is left with a set of information that paints the picture of what happened. So the Movellus Aeonic Insight module is able to detect the voltage event when it happens. So it essentially gives the moment when it happened and what happened. And then the Tessent Embedded Analytics, once it's enabled, can further complete that picture and give an idea of why it happened. So in terms of actionable insight, in this case, in this example that we created here with the Movellus model, so we could see that the data collected, we could see an increase specifically for core 0. So that would identify the potential source of the problem. Then the user can also observe what the level of the buzz usage correlates with that problem. So then it has an idea of what level is sort of the danger level for this event to occur. It also has information regarding the behavior of the voltage throughout. So it has what was the minimum value observed and when it was observed. And then finally, the user could then take mitigating actions such as rebalancing the workload, even reducing the workload to a safe level. So throughout this presentation, we demonstrated that having a multi-instrument approach to monitoring complex systems is not only desirable, but it is also possible. And so we can get information to detect, understand, and then act upon in life, in a solution in field. Yes, and with that, we conclude the presentation. Thank you very much. If you want to hear anything else that we've mentioned in this presentation or anything else regarding Tessent Embedded Analytics, please visit us at our booth. And thank you very much.